Hi, so I will probably start my presentation. I'm a second-year graduate student in the Department of Bioengineering, and I'm co-advised by Professor Kong and Professor Bashir. So today I will talk about my project, which is engineering a functional neuromuscular junction using nanotopographical substrates. So I will tell you what I have been doing and eventually what I'm going to do in the future. So muscular dystrophy or related neuromuscular diseases often result in muscle loss, and it's a very common disease. So 1 in every 4,000 to 5,000 people in the United States suffer from this disease, and the estimated cost of illness is about $1.3 billion to $4.8 billion per year. And one of the biggest problems of this disease is that there's no therapeutic drug that can stop the muscle loss in the body. So one of the solutions I came up with was based on this paper. And this paper was about engineering a muscle tissue that is capable of releasing insulin-like growth factor 1. And this growth factor is capable of inducing muscle growth in the body. So they engineered the muscle tissue that can secrete IGF-1 in the body. And by co-culturing this engineered muscle tissue with a normal muscle tissue, they observe how the normal muscle tissue will respond to the IGF-1 secretion. As a result, they could see that the normal tissue culture with the IGF-1 secreting muscle tissue was enlarged in the size. However, the limitation of this paper was that they mostly relied on a sustained release, and they weren't really able to control the release of IGF-1. So the solution to that paper I came up with is engineering a smart muscle tissue, and that releases growth factor in a stimulus-responsive manner. And I would like to achieve this controllable system by introducing a neuromuscular junction. So neuromuscular junction is a chemical synapse formed between the motor neurons and the muscle cells. So upon receiving some signals from the motor neurons, the muscle cells can contract. And there have been some studies to engineer neuromuscular junction in vitro using C2C12s and some neuron cells. However, the limitations was that they were only based on observing the morphology of the neuromuscular junction, and they haven't really used this system in a drug delivery device or engineering some smart tissues. So my primary goal is to engineer a smart muscle tissue that can release growth factor of interest in a stimulus-responsive manner. So if you see here in this cartoon, without a stimuli, it will release some growth factor, but upon receiving some stimulus to the motor neurons, they could probably release some more amount of growth factor to the adjacent cells. And my goal is based on two hypotheses that that muscle cells will align better and form better neuromuscular junction when they form alignment. And the neuromuscular junction formed on the top of this muscle cells will probably have more control over the muscle contraction. And it will probably elevate the release of the growth factor from the muscle cells. So my first aim is to engineer a aligned muscle fiber on a nanotopographical substrates. And the reason why I use nanotopographical substrate is that there were some studies that showed that some nanotopographical substrates can induce enhanced myogenic differentiation level of the muscle cells, and also it could induce the contraction of the muscle cells by making the cells to align on the substrates. And as you can see here in the diagram picture, the myosin filaments range between 12 to 18 nanometer in diameter. So probably some bundle of myosin filaments will be around 100 nanometer in diameter. So probably my substrate will be able to form proper environment to the muscle cells. So I will show you my results. So my first aim was to prepare the substrates and look at the morphology. So this is the preparation step. We created a silicon master, and by putting the polyurethane acrylate resin, we could fabricate a pattern substrate. And in order to culture the cells, I coated the matrigel on the top of the nano pattern. And the bottom here shows the morphology of my substrates. So this is the unpatterned substrate. This is the 200 nanometer substrate, and this is the 1600 nanometer substrate. And the width of the ridges and grooves were the same, and the depths were all same as 600 nanometer. So 200 nanometer scale would be both 200 nanometer ridges and grooves, 1600 nanometer ridges and grooves here. And as I cultured the primary myoblasts extracted from mice, we could observe that the cells cultured on the nanopattern substrates show much more myosin expression level compared to the flat surface. So, and also, as you can see here in the right, the myotube width and length and fusion index was also very high in the nanopattern substrates compared to the flat substrate. Although there were some variation here, it didn't show a statistical significance here. So, and also it was interesting to see that the cells grown on 1600 nanometer patterns showed more differentiation level as well as some elongation in length and fusion index. Because there has been some studies that showed about 200 to 400 nanometer patterns are very effective in inducing myogenic differentiation, but it was interesting to see that larger nano pattern could induce better myogenic differentiation in my study. And this is the contraction. We also observed the contraction level of the muscle strips. And you can see here that the cells are contracting in a very random manner. And the cells here in the nanopattern substrates are kind of contracting in a more uniform direction. And also the cells cultured on the nanopattern substrates show slightly better, slightly higher contraction frequency compared to the unpatterned substrates. So this is the results I have so far. And the next step would be studying the intracellular molecular reorganization, like actin and integrin, like how they are formed on the nanopattern substrates, and study some molecular level effect on the cells. And after finishing up my first aim, my next aim is to engineer a neuromuscular junction on my muscle cells. And I will probably use a neurosphere differentiated from embryonic body. So by introducing the neurosphere to the muscle cells, we could probably induce neuromuscular junction formation. And I am assuming that my nanopattern substrate would enhance the neuromuscular junction formation compared to the flat substrates. So my plan is to do some morphology analysis using immunofluorescence imaging. And also, I'm planning to introduce some glutamate or any other available chemicals that can stimulate the motor neurons to release the acetylcholine to the myofiber and control the muscle contraction. Oops. I think the video is not working, but we also have done some preliminary studies, and seen that the embryonic body could actually stimulate the muscle cells to contract. So the significance of my study would be developing an active and controllable delivery system in the future, and understanding some underlying mechanism of the neuromuscular junction formation using my nanopattern substrates as well as the myoblasts and ESC-derived motor neurons. And in the future, I'm planning to probably incorporate this neuromuscular junction system into a smart delivery vehicle and deliver some protein of interest to the in vivo system and study how that works. And I would like to thank my advisors and my group members, and also Professor Seong-Gap Im and Seung-Jung Yu in KAIST, who provided me with the nanopattern substrates. So, thank you.